Again, disappointed a little that there are no students, but what I was going to do is I was going to talk about n-ellipse in a very simple way. So yeah, so I decided to do this activity based, right? Let's try not to use equations, only diagrams, and maybe. So I will change my camera a little bit. So this is just my table. Okay. So what our goal is to have draw a circle. So what I will say is, let me have a pencil if I can find one. Yeah. So I'm going to set n is equal to 1. Is this readable, by the way? I can zoom it in.
Yes. No, Shajesh. Yeah. This is yeah. It's fine.
Better.
Perfect.
Okay. So what we are going to talk about is n-ellipses. So let's just. So n equal to 1 would be the usual circle. Okay. And n is equal to 2 would be an ellipse. An ellipse is slightly squeezed circle, if you want. So just a simple circle. I'll make this more precise in a few minutes, and then I would like go into activities. And an ellipse is sort of an egg, if you want. So that's an ellipse. And the idea is that what does this mean? N equal to 3, right? How do we define that in general, right? So n equal to 4 and so on. So that's pretty much the goal. But let's say, so oops, I wanted better. Okay, so I have a thread here, right? So this is how I'm going to do a circle. And what I did was I took a small box and made holes in it, so that you'll see that there are 3 holes in here, and that will play an important role. As I increase n, that is what is going to happen, n equal to 1, n equal to 2. But as of now, there is only one. This is basically a simple screw. And this is where the students come in. I think I was hoping that we can have better ways of drawing a circle, right? So the first question we can ask is, we all know a circle, or first let me draw the circle, let's say. So I put just so that it becomes neater. So I put a paper in here, and just to make this length of the string smaller, I make double this. So this is my string, right? So I have doubled it, and maybe make it smaller again. So this is a simple string that has been, where is the camera here? That has been made into a circle, or a finite length, right? Put it on one end, and I use a nut so that I get some control on this. Yeah. So that's now stretched. And now I draw this. This should be very obvious for us. So that's a circle, right? Right. And I'm not finishing it there because the paper ends there. Now, what is the definition then is, one definition is that the distance between any point on a circle and a fixed point. This was, I chose this point anywhere, right? I could have started from anywhere, and I want all the points that are equidistant. You can think of if you tie a cow to a pole in a grassy land, you will notice that all the grass is eaten up in a certain region. Whatever is left of that circumference is basically a circle. So we will call this F1. So this, I'll call it F1. It means focal point 1. So this will mean focal point 1. So focal, is this readable? Focal point. So that's F1. That seems obvious at this point, but we'll have more focal points, and that is where we generalize. Just as none of students I know here, but I think between us, I was thinking we should all take it as a challenge and ask ourselves, how many ways do we know, or how many independent ways can we draw a circle? Like, this is one way. Is there any other way you can think of drawing a circle other than copying something else? Like, for example, you can take the lid of a cylindrical jar and place it and trace it. That we don't allow it. Like something like this, there is a rule here, right? The distance between these 2 points has to be fixed. So in that spirit, how many different ways can we draw a circle? So that's, I think, all of us, it should be a challenge for all of us. It doesn't matter where you are, and one will quickly realize, I was thinking it for myself, and I quickly realized that I don't know more than a handful ways of drawing a circle, right? So that should be taken as a challenge. So I want to stress something in here. So one point that comes out.
What are the other ways?
Oh, the way I was looking at, okay, one of the ways I thought about is that if you take the set square, what do you call that in the pencil box that comes in? Basically, one of the angles is 90 degrees, and the other is
set square. Set
square, right? So keep that. Remember that what I was using there is that if I draw a straight line here, and any triangle that you form will always have 90 degrees in there. So I was thinking I can use that as a principle, have a triangular structure there, fix that, and since one of them is 90 degrees, the other 2 points have to be on the circle, and then I rotate them. Right, that's another way I was thinking, but I am more imagining. Notice I'm not experimented with it. This is one of the things I've experimented, and I'm clearly not having too much experience in that. But I think what I was trying to tell is not to address them here. If one thinks that this is, or I was trying to challenge myself as to how many ways I can draw a circle, and I couldn't come up with many ways. Like, it was handful, like less than 5, at least when I thought for about 15 minutes. But yeah, what I'm trying to say is that it could be challenging just to think along that line, and that's the way I was planning to address that to the students. So yeah, I don't have an answer, because obviously that list will be long, right? So I cannot answer that question. I don't have it clearly. Does that help, Raj?
Yeah. Okay. So basically think of other geometrical properties of a circle, and then probably there might be some hints, right?
Yeah. And then, of course, the point comes, right? I think this is the way I think it goes, is that in principle, circle probably has one central definition. Doesn't have to be that the fixed radius is fixed. It has one central definition, and it can, rest everything can come. So now if you have 2 ways of drawing a circle, whatever principle you're using, they are connected. So then there must be some theorem. Then you basically know that that result is true, at least geometrically speaking. So then you know what to prove, at least. So that could be one strategy one can build to discover problems, in a sense, right? If you're not having sufficient problems to work on, then if you can do it in 2 different ways, then those 2 must be related to each other. So prove that one is related to the other. So in this case, so that is, I'm thinking along that line because I have this, one way of looking at is that a circle also has, think of this as the radius. And at this point, I can draw a line that is going from F1 going out, and I will call that N1. And I want to choose this to be of unit length. So this length has to be fixed. And I choose that to be of 1 unit. It could be 1 centimeter, for example. And that hat means that it is of fixed length. It is of unit length, and that is N1 hat. Okay. And in this case, it might come out trivial from our learning process, but later on, and I'm generalizing this to more number of ellipses, it will come out that this will be, in this case, it is, we know that this is perpendicular to this tangent vector. So this is called the normal vector of a circle, or the radial vector. And the tangent vector is in this direction. So, and I will use the letter V for that. It should be T in principle, but I think since you're in physics, you tend to think of this as a trajectory, and I will associate the word V in here. And V and N here are perpendicular. So there is a normal vector and there is a tangent vector, and they are perpendicular to each other. And this condition, I'm going to say, is going to decide that, or I can make a proposition that, can this decide the circle? Right? If I know that this is at least a set of circles, if not one particular circle itself, at least a set of circles can be. Here again, this comes out reasonably straightforward. We know the circle that normal vector and tangent vector is fixed. Remember again that this has this r equal to a constant feature. That imagine you remove that r equal to a constant feature, and you want to think in terms of the condition that the normal vector and the tangent vector is really perpendicular, can bring out this feature or not. And that raises the question, how do we find the normal vector? Here the procedure was start from F1, draw a line, pick any point in there, and have a unit line coming out of it. And let's now do this for ellipse, and hopefully I can bring out more richness in there. At this point, it comes out a little straightforward. Any questions here? So this should be all. Probably I'm still introducing the problem. Any questions? Can think of? No. Okay. Okay. So next, I want to do this for 2 spheres. So let me change this to, I want to put in another so I put in the second item this. Okay. So now we have 2 of them, and I again use a paper so that it's cleaner. I tried erasing these things. Okay, so and now let's have the same thread, and I want it to be a fixed length, so I make it a little wider this time, and that stretches it here, and I want to make this a little smaller. That's too small. Okay, we'll keep it as it is. Let me see. Probably it's okay. So I use the small nut to just for control of the pencil. So stretch this. Now notice what is happening is that the only constraint I put is that the total length of the string is the same. And I stretch this and go about it. Paper is not sufficient. And this looks from a very far point a circle, but you will notice that we have squeezed this a little bit in here, right? So that is a little squeezed. But now let's.
If you probably tilt it a little bit so that the foci are, yeah.
Make it better?
Probably a little better, yeah.
Little better, not a. So maybe I should put it at a farther distance. You want me to try that now? It might be more effective, I think.
But what do you mean by farther distance?
If I put the
foci
farther distance.
That might be better. Yeah.
Put the foci farther apart.
Yeah, so that will be harder because now I need to have a way of making holes. Actually, more than that, I can make this small. Like, let's keep this the same. Okay, I think that's better.
Yeah, that's easier.
So let's make the string smaller. Why change the foci?
Yes.
Right. So let's have.
You can put a knot. Put a knot in
just
between.
put a knot there, right?
Yeah.
Okay. So it's right, and let me cut this out. So okay, so again, I stretch this. And that should be better, I think. You want it straight, right? You tilt it a little, and that should convey the point that it is a squeezed circle if you want, but not squeezed in any sense. It is under the condition that this length has to remain exactly the same. Okay, so that's how you, so this is an ellipse, and that's a way of drawing an ellipse. And let's now see if I can convey what I was trying to propose. So this is F1. Let's call this point focal length 1, and that's focal length 2. Pick any point on the circle, let's say this one. I put not the circle, on the ellipse, and draw a straight line from there going outward, and that's my N1. This time it is N2 because I chose the second one. So it's N2. Do the same thing from here. And that's N1. And again, I want to choose this length to be of the same amount. That's what I define as the unit circle, and choose your unit, but it should be the same. So that's N1, and n2. And you will notice that just visually one can see, since I have already drawn the ellipse, that both n1 and n2 are not perpendicular, or doesn't seem like it is perpendicular to this trajectory or the path along which the ellipse is. But very under inspection, but like I can prove this algebraically, what I noticed is that if you were to draw a parallelogram here, which vectorially means that this is you're adding these two vectors. So that's that vector here. So that how I have drawn that is that complete a parallelogram out of that and connect the one corner to the other. And that you define as your n. So now our equation has been, if I'll write it here, not necessarily a unit vector. So this is n1 hat plus n2 hat. Okay, this will be always perpendicular to this path, okay? n1 plus n2. And that means to say that if I were to draw the velocity vector here, that's a tangent, right? So that's v. So v dotted with n is equal to 0, right? This is using some principles of vectors. This means this dot here means that they are perpendicular to each other. Again, draw.
Actually, dot doesn't mean it, but yeah, if that equation means that they are perpendicular. Like if the dot product is 0, then they are perpendicular to each other.
Oh, correct. Yeah.
You want to complete this statement.
Yes. So yeah, good point. So I meant to say that if the, yeah, so this is a symbol saying that if this kind of product between two quantities is 0, then they are perpendicular to each other. In general, they are not 0, but if it is 0, or whenever it is 0, that suggests that this might be perpendicular. At least that's one of the solution. Okay, so now so this is the relation, if you want, and then the question is, which one has to investigate more carefully, is that from this condition alone, can you draw the ellipse? Like, does this serve as a defining property of the ellipse itself? And you might see where I'm heading on to. Like, I've done this for 1, 2, and you put in a third focal point, and you draw n1, n2, n3, and you will add up all these 3, and that's where I'm heading towards. But
I have a comment here.
Let's have a discussion. Yeah. Yes. Right.
So yeah, I mean, mathematically I understand it. But you realize in this case that getting your n1 and n2, knowing the ellipse, basically knowing the two focal points.
This point is necessary. I agree.
Yeah, is important, because you can have a multitude of vectors which are perpendicular to each other. The trouble is, like, whenever a vector is given, there can be infinite ways to resolve it in two directions, any two directions.
Yeah, but there is always an initial condition, right? So I was thinking how you can go about that is that when it is along the line, correct? So think of a if you are having a computer and you want to draw a trajectory, you have an initial condition. So along the line, n1 and n2 are along the same line. So I know this point to begin with, somewhere around here. So that will be my initial condition, if you want. Like somewhere I have to say that, okay, the ellipse surely passes through this point. It's an initial condition. And then the question is, okay, how do I draw the next point? So I'll say that, oh, okay, this is a perpendicular vector. So I go here. So that's a tangent vector. So I go 1 point. So it has to be close enough. It's idea of calculus you're using. So you get the next point, like computer can draw that next point. And then from that point on, now I have a point, correct? from that point on, I use this algorithm that get me n1 plus n2, draw the perpendicular line, draw the velocity, go to the next point, and keep going that, iterate that many times. That's, I'm sure that I might be missing things. I haven't gone over that a lot, but yeah, that's my, so yeah, you're correct that it seems like, how do you know the point, but you need one initial point answer. Yes, so there is an initial condition somewhere that it passes through this point. Otherwise, there is a set of ellipses that will be satisfying this.
So now that you have said that calculus, then probably calculus can do the job, right? Because you have to think about
Of
D in
course,
vector, right?
yeah, this is from the perspective, if you think of it algebraically, that's a completely different perspective you're bringing in to the problem. Like my way of saying, or the way I'm addressing this is that we know these 2 points, and yeah, let's say without, I'm not sure how precise that is. Without the idea of calculus, can you draw an ellipse, or can you draw figures without the idea of calculus? It's like saying, what is the maximum value of a function? Calculus, of course, gets it, but then are there, or put it like this, before 1650, right? Like 17th century, when Newton brought in calculus, were there not ways to draw ellipses or circles, or finding the roots of a equation? There must have been, and they were mostly geometrical. So, or a little bit of algebra just developed at that time. So that's the point I'm trying to make. Does that help? Yeah. Maybe not very useful.
Yeah, no, it is helpful. I was just thinking like maybe there are other geometric properties that could be also. Like in the case of the circle, you told us, right, that the angle is 90 degree always. Then the other 2 points are like, if it is a semicircle, then there is always a right angle triangle in that region, right? So same way, like maybe there are geometric properties here also of circle that can be utilized. But this is interesting in the sense, yeah, this is a very precise definition that you're bringing in. But that the point is like, yeah, it does depend on some math that you have to do. Not like purely just take a string and draw it. That's the definition of a circle or an ellipse. But that was more of a comment, yeah, like, yeah, please continue.
Okay, so let me proceed and finally do the 3 case also. I can draw that, but before that I can at least point out. So the claim is that, and if you, since we don't have any students, I can very quickly say how this comes about. If you have a focal point, if there are n focal points, f1, f2, and f3, and so on, if there are n focal points, and so let's say this is f1.
Not necessarily collinear, right? Oh.
Not necessarily collinear, yes. So this is, and put them as vectors. So you have f1, that's f2, but they're all on a plane, let's say. Okay, good point. Does it have to be on a plane? In the next line, I might be able to tell it. For now, let us say that it is not on a plane, but I have been thinking about all through as it being on a plane. And again, there are many other points. Have another general point here, let's say. So that's your R. Right, so that means to say that this is your origin. So that's your F1, that's your F2, that's your F3. But I'm interested in the relative position of this R. So R would be, so that's your origin point. So this is R minus F2, for example. So R minus F1 is this line here. Right, the difference between the 2 points. R minus F2 is this, and R minus F3 is this point here. That's too much clutter at this point. But now what I'm trying to say is that the length of this, the length makes it a magnitude. So R minus F1 plus R minus F2 vectorially, and then you take the length, right? And not sure if I lift it off the surface, what are the consequences? This definition can stay, I suppose. So this is F3 and so on. That's equal to a constant. Right, that's the definition of an n-ellipse, if you want, like one of the definitions that you can begin with, that you pick n focal points, very simple. Then the distance of an arbitrary point, if it remains a constant, so it's a loci, then you have the definition of the ellipse. Let me give this a name. This is a small r1, let's say, plus r2. So this is the length of the string coming up, right? So if I have all these lengths, and that has to be constant. We did this for only 2. If you can imagine this happening for a more number of points, then you've defined an n-ellipse. But from that point on, how do you get whatever I was saying? It's only 2 steps, basically, even though in the beginning when I did it, I went around in complicated ways. But eventually, I think it is pretty straightforward. This is a distance, then the change in this distance when you're going from one point to the other. So if I go from here to the next point, right? So this is a trajectory that has this fixed. When I go from one to the other, so there is a calculus there that change if I were to make. So this is d of r1 plus r2 plus so on is equal to 0. Right. So that's there. At this point, this is perfectly fine, but I haven't gained much information. Divide this out like by the small coordinate. Now this is dr, not r1, r2, this is dr. And take a dot product of that with dr. I could have divided it by time, since I'm in physics, I think of it as a trajectory. Yes.
For some, for some reason, your camera is focusing back and forth.
Oh, on my hand, maybe, right?
I think it is on autofocus. The more he moves his hands and everything around.
Yeah.
He has to take the camera off the autofocus. Yeah.
Okay, I should take that off. Okay, good.
Yeah.
Good point.
Focus it on the paper and then leave it there.
Yeah. Okay. That's
because if you try to find your hand and try to focus on your hand.
Got it. Okay.
Yeah.
Okay. Thanks. Okay. So this is not the best way to implement this. Yeah. This is a bonus. I was trying to make this on the on my blackboard, and I thought, oh, I just have to turn the angle and I get it on the table, and it could be useful. So the first time.
It's nice. This is perfect, Shajesh. No issues. This is perfect.
Yeah. But okay, so think of this as I'm dividing it by time if you want, and then use the chain rule. Then I get the dr by dt. But now you get this clearly that this is dr by dt, and this is velocity, and this is nothing but gradient of r1 plus r2 plus so on is equal to 0. And that tells me that this is n1 plus gradient of anything is always a normal to that surface. So this is v dotted with n1 hat plus n2 hat plus so on is equal to 0. Right? So that's sort of, when you eventually do it, that is all there is to that's very it should be very straightforward and a kind of a defining property of an n-ellipse. Any questions on this before I try to really draw this for the third, with the third focal point? And then it becomes a little challenge because then you have to come up with a trick to do it.
I think that is good, but I think but dividing by dt was to just get this velocity, right? I mean,
Yes.
there is no other way to just like leave it at dr, which is displacement. Probably you don't want to leave it at displacement.
No, this is okay. The way I did it, this is perfectly fine. This is dr is a tangent vector, right?
Yeah, but maybe the
But I was
velocity
trying
in
to
physics
motivate
is more precise definition than. Yeah.
Yeah,
The displacement is there. You will have to just leave it in incremental.
correct. That's
Vector.
okay. But I think when you're dividing out by a displacement, that's a little more abstract, or that's harder to imagine.
Well, it's
If
not
you divide it
dividing
out
out
by a
by.
scalar, it's easier, right? Dividing out by a scalar is much nicer. Right. So, I mean, what I was trying to say is that if I have this, right, that is equal to 0, that's perfectly fine. By dividing out by vector, I might have more imagination problem, but if I divide it out by a scalar dt, I'm very fine. I think that's, or at least maybe it is a physics background that it makes it easier to visualize it. So this is easier for me to visualize. And then I say that I use a chain rule. But so inbuilt, I'm using all this calculus
I think
properties.
d by dt is d by dr and dr by dt, right?
Exactly. Yeah. So this then I say is in 3 dimensions, dr by dt. Got it. So it seems like all this goes through for 3 dimensions, right? So it seems like so are we suggesting that
That is okay, right? Because the total derivative with respect to time can be broken up into 2 pieces, right?
Correct. This is fine. Exactly. Yeah. So that's what I'm saying. That's a chain rule from here to here. It is not very hard to, like, again, if you're algebraic, it is not very hard to see that. But probably if you want to intuitively see this, it might be harder. But my point was that you raised a point somewhere, I think in this discussion, it came out that what if these points are, yeah, it was Rishi who asked that is this collinear or not? And I thought, oh, is it on the plane? So apparently I haven't used any fact that this should be on the plane. But of course, if you have 3 points, yeah. So is it true that, first of all, ellipse, is it well defined?
Actually, you can take it anywhere in space, but you will always, if it is a 3 points, then you will always be able to draw a plane through 3 points, right? I'm not sure if that is the true fact points. About like if you consider so anything beyond 3 is probably not possible, right?
But apparently here it is possible. n-ellipse is defined this way. If I say it is defined, apparently.
No. What I mean to say is that, like, I mean, anything more than 3 points need not be on the same plane.
Oh,
like
yeah.
Three can be on the same plane, right?
Yeah, I can choose a plane which contains all 3. Yeah, correct. There exists a plane which has all 3. Correct. So.
But suppose if your third point is okay, 3 points will always be in a plane. You can always find a plane through. But if you have more than 3 points, then what you have is not a curve, but a surface passing through those points, right?
Correct. It is not.
It will become a surface. Yeah.
So yeah. I don't want to say anything, but at least when I'm looking at this set of equations, this very easily generalizes to going off the surface. But I would imagine an ellipse itself, the condition R1 plus R2 is a constant. So that leads to a lot more points than just the ellipse itself. Correct? If I go beyond on the surface of the plane, there are more points, right? It is very easy to see that here. So that is, if I were to put this in here, right, I fix this, and if now I'm pulling it up, right,
Mhm.
So that's also, now I have a way of generating a surface on in 3 dimensions, right? And that won't be an ellipsoid, I suppose, right? Or is it? Is it an ellipsoid when I do that? I think maybe it must be.
Yeah, it will be the ellipsoid of revolution.
Tell that again, Rishi. I think I didn't.
Revolution, like
Oh, revolution. Yeah. So will it be
Ellipsoid of
the
revolution.
same thing, ellipsoid got by rotating it about the line connecting that? That must
Yes,
be.
exactly,
Must be,
exactly.
right. Okay.
Yeah.
But then it's not very obvious in the 3 ellipse, right? But let me quickly in the very end,
Yeah,
at least, yeah,
Shajesh.
quickly, yeah.
Yeah. You know, just to address the Prachi's earlier comment.
Mhm.
So I think this is a nice construction in the sense that, you see, given 2 points, okay, as Prachi said that you need to know the ellipse, draw N1 and N2, right? That's what she said.
Yes,
well, if you're thinking purely geometrically, that could be the situation. But yeah, if you bring in calculus that you are doing incremental tangent vector.
No.
Then-
Actually, the point is, given 2 foci, the ellipse associated with the 2 foci is not unique, right?
No, that is true. It depends on that length,
So-
right? That's what the Shajesh, like that's what
Yeah,
Shajesh is saying.
So the point of this construction, the way I see it, is that given 2 points F1 and F2, okay, now you take a third point, which is not collinear with F1 and F2, okay, and then draw 2 lines, 2 straight lines passing through that point from F1 and F2, okay.
Mhm.
Now, the line which bisects the angle, okay, so you have F1 and F2. Now you take a third point randomly, okay, which is not collinear with collinear. Of course, also you can do that, but even if it is not collinear, to the third point, then draw a line from F1 to the third point and from F2 to a third point, such that they extend by, say, unit vector outside of the third point. Okay. Now, find the bisector of this angle and the perpendicular to that bisector. Okay. The curve which is tangent to the perpendicular to the bisector will be the required ellipse.
But is it always true that it is going to be like in every case, like maybe ellipse is probably maybe easy to visualize, like is it always going to be the bisector?
Yeah, it has to be a bisector.
Yes, right.
It has to be a bisector. So you can choose that point wherever you want. You don't have to know ellipse in advance.
Yeah, but consider the other one. Like, I mean, now Shajesh is going to bring like more than one, like these 2 foci, right? Like, I mean, he'll bring like n, or like 3, 4. In that situation.
No, so the derivation clearly tells us that, there is no, unique point that, so it will decide the shape, okay, because the length will change. So it will change the shape, but the gross properties will not change. The geometrical properties, just as different ellipse.
Like the way I understand this thing is that any tangent vector, like any perpendicular normal vector to a path, that always passes through like, I don't know, some circle, like some any curve can be fit to a circle, right?
No, this is not a circle, right? Because
this is not a circle, Shajesh, but the tangent vector to, like, sorry, the normal vector to that path can be.
Because there is no center now, right? Then the moment you say circle, there is a point.
Just a minute.
Like Shajesh, it is not in the middle, but yeah.
Go ahead. Just a minute. I'll just be back in. You go ahead.
Yeah.
So I was just going to say is that, like, I mean, whenever you have a normal vector to any path, any curved path, you can always think of that tiny portion to be a part of a circle, right?
I think I'm confused a little.
Okay, consider any tiny section of any curved path.
Yeah.
That curved section can be fit onto a circle. That's how you define radius of curvature.
Or you can fit in a circle to 3 points very close like infinitely close 3 points, you can fit in a unique circle to it. But you cannot fit in a circle to a curve all the time, right? A curve is
It will always be,
only tangent.
No, it will always be true, because like, I mean, that is how you will define your radius of curvature, right?
Correct. I
Like
see
if
what you're
it
trying-
is a curved point, then it should have a radius of curvature,
Correct. I agree.
right?
Oh, so what you're trying to say is that this n defines the radius of curvature. Yes, that's correct.
Yes, and that will be the, like, I mean, the direction. Okay, so radius of curvature will be from some center, right? Some center to that point.
No.
It will be, Shajesh. Like, what do you mean by radius of curvature? The radius of curvature of a curve means that at that tiny point, you can actually draw a circle, and that circle has a center.
Yeah, but that center doesn't have to be the same all the time everywhere.
Yeah, it doesn't have to be the same.
I agree.
It doesn't have to be the same all the time. All I'm trying to say is that the direction, like line of that center, what do you call? Like the direction of that center defines your n. Sorry, direction of the line joining the center and the point defines your n.
Correct. I agree. That's what it's, yeah.
But yes, the only point I wanted to make is that one does not need to know the ellipse beforehand in this construction. That's the only point I wanted to make.
Yes, yeah.
You can choose your point and define your n1 and n2 as two unit vectors, emanating from that point with respect to straight lines from f1 and f2, and bisector of that angle between n1 and n2 will define the tangent to that bisector, and the curve which is tangent to that at that point will give you that, and then you keep doing it and you get it.
Correct. Yeah, basically do it in the next one and keep doing that. So basically the locus of this tangent lines itself brings out the. You will need to use calculus, simply because, I mean, the circle is the curve of a constant curvature, right? So that's why,
Rishi, I have a problem with that. Okay, so the point is, like, you can take one point. I agree. Like, you can take one point, have your n1 and n2 defined precisely because the foci are given. You can have it. Like, what decides that the other point is not way anywhere on that plane, and it has to be like right on that path? Like, that's where the tiny tangent vector point is much more precise in defining. So, like, you will again have to go through the next step, which Shajesh says that, yeah, tangent vector, once you have decided your tangent vector, it has to be like incremental. The next point has to be incrementally next to that. Like, I cannot just randomly choose next point anywhere. It has to follow this tangent vector's trajectory.
Yeah. So actually, yes, Shajesh, the point is, so the first point that we choose will decide one of the ellipse, but since we are starting from scratch and since the curvature is not constant, in the case of circle, the advantage is that, if you can draw it locally, you can draw it globally because the curvature is constant. Okay. But ellipse, the curvature is not constant, and that's why what will guide the choice of your next point?
Yeah.
I mean, of course, if you use the property that, you choose the next point, okay, so one will have to, of course, choose the property that choose the next point, which is the same distance, whose sum of the distance from the two f1 and f2 is same. If you use that property, then of course.
Yeah, but then you're using the f1 r1 plus
exactly.
r2 is equal to constant. That's not okay. But that's where the calculus will come in. I mean, it will get more and more precise as you make it smaller and smaller. So technically that cannot be achieved very easily. But otherwise, I think you will go away from the.
Like what I was, I think the debate here is that it's like not completely what you call.
No, it only requires a
geometric thing was like the geometric thing was that your r1 plus r2 has to be constant, and then you draw it using that. But it is kind of using the,
But that is where the challenge comes, right? So now, I mean, I think you guys have addressed this properly. Using this perpendicularity alone, can we draw it? So we just have to be clever enough to come up with a technique that uses this perpendicularity to draw the ellipse. It's just that we are not able to do it, but there must be a way to do this because it's a property of an ellipse. It must be possible.
Shajesh, the challenge is, challenge is to nail it down to the
Precision.
given ellipse, because
Correct.
because given f1 and f2, you can again have the same perpendicularity property for another ellipse, right? So there are infinitely many ellipses which can be drawn about f1 and f2. Okay. Now, and all those ellipses will satisfy the perpendicularity, right? Between n and v.
Yeah, but you can always say that next to this point, let us say you have a circle of points. Don't need circle of points, many points, let us say. And you pick that particular one where you're actually perpendicular to this. Like that's one way one can think of proceeding. Like, does that?
No, it will not. I don't think that will. Simply because your rate at which your normal vector is changing its slope is not constant, and
yeah,
that rate of change of the slope of say v or n whatever will be decided by the eccentricity, and one point on ellipse will not decide the eccentricity, because eccentricity is you need in a infinite, and you cannot decide based on one point the eccentricity.
No, you can decide the eccentricity using one point.
Just a minute. So what is the formula for E eccentricity of the ellipse?
It is decided by the
ratio of that
focal length and the length of the string decides it. Definition is 1 minus
fine.
over
then Shajesh, we are using, my point is that so that is tantamount to using the fact that distance of that point from f1 and f2, the sum of the distance from f1 and f2 is constant. If you use that fact, of course, then you don't have to. Then that property alone will decide your next point.
I agree, but we don't have to. I completely agree that that's a challenge. Yeah, so we do not want.
My point is that short of that definition, can this perpendicularity alone tell us where the next point would be? And as Prachi rightly pointed out, you can draw one point which would be on a given ellipse, but you don't know where the other point would be.
Correct.
And I don't see it how calculus will also get you, because to get there, you have to know the rate of change of slope, and to know that you have to know the eccentricity. To know that you have to know some condition which defines how the second point is obtained. Which is exactly like the sum of the distance of that point from f1 is same. That's the defining condition. Otherwise, you can draw infinitely many curves of varying curvature. But ellipse is a specific curve with a property called the fixed eccentricity.
I agree. Yeah. But that is not what I'm addressing. But that's a question I have in mind. A broader question is that's what comes out of this.
This was just a curiosity that I had. That it would be nice if using this property itself you can decide the entire ellipse. But at least at this point I'm not able to see how we can do that. But it's a nice construction. But it's a nice way to understand the relation between how does the perpendicularity condition. So basically, an ellipse where you have 2 points, they will you have two n1 and n2 which will move equally away from the given normal. So it's a nice way to understand that.
So let me quickly just finish it up. Let me draw the third one also, and that itself brings in a new challenge of how do you draw this. right? Earlier, that's at least one I think you can just wrap it around 3 times and it goes through. It seems to be okay. That's what I used, but nice creative ways of drawing itself might be interesting, I suppose. So let me.
So I'm curious to see what does the shape look like.
Oh, the best is to go into like this. Doesn't bring out the does justice to the richness of this curve. What I did is I went to Mathematica, and these days you can really have a lot of freedom in there, and you can change the focal points wherever you want to, and you really see the structure coming out nicely. But here it will come out a bit, especially because I've chosen 3 points in a kind of an equilateral, so it will come out very slightly deformed circle. It doesn't do justice. But the main point is how do you draw it, right? I think that itself is a
Yes.
so let me do this. Make it a little shorter. So one has to jump from one to the other. So
if you give it a twist at all the 3, one twist in all, will it work?
yeah, that's how I managed it, and that seems to be sufficient. But we struggled with it for some time in the beginning as to how to achieve it. Going to simple Google search, at least more than one place, but it might all be the same source, say that it was done apparently for the first time by Maxwell at the age of 16. I'm not sure. It is not very convincing to me immediately that it took all the way till 1865 or 18, like Maxwell, a 16-year-old, probably in 1830s or something, for a 3 ellipse to be drawn in a convenient way. That's not very, or it's not convincing to me. But
it must have been considered before, I'm pretty sure.
yeah,
Maybe the
maybe
written,
Maxwell did do
written
this,
record is
but
not there.
Shajesh,
probably not the first person to do it. Yeah.
I
Yes.
think the way to understand history is to understand that all history is only the recorded version of the history, which is sort of a very small percentage of the actual history.
And that's not the only thing, Rishi. The point is who is recording it. So every king recorded the history in their framework.
I'm saying that even though that is always given, the history is always viewed through some lens with a tint.
Yeah.
But I'm saying that even if you take it, it's still they recorded, and there is a much larger portion which is unrecorded.
Yeah, definitely. I mean, all I was trying to point out is whatever is recorded is also not the like what you call a neutral lens. It is also a very, very biased lens.
That is given. Human being has to view it from the perspective that one has. You cannot free.
Okay, so let's try this. This is going to be difficult. And it needs more trick.
Maybe again you need to have a smaller string.
No, I had to go double, right?
Then create another one, but yeah, anyway, go ahead.
Now let me try this. Okay. This gets tricky. So that's 2 of them, correct? That's 2, but now I need the third one. Sorry.
Yeah.
There you go. Okay.
Don't lose it.
Yeah. Okay. Okay. So this is
Yeah.
stretching all three. I have to do this a little slowly, and I think I might be able to get it only one side because someone has to come and. Okay. I'll try. Okay. Is this clear enough? Stretching three. And
Yep.
I just move it, but I can go only within this region. After that, I have to change this. So, okay, so this is mine. Oops, not a very. Notice now it gets blocked, right? The moment it.
Hmm.
So I have to now lift this and put it on this side. And now it has reached here. So this I have to lift it and put it on this side. So that's the inconvenience. Oops, now it's. So now it's getting looser. Oops.
Oh no.
Okay. Not the best. Okay. Okay, I give up. But okay, how about this? No,
Show us a picture from the Mathematica if you have printed it.
No, I don't have it.
You don't want to. You don't have to.
I
do
don't
it
have
yourself.
it.
Print it.
I can
I
try
thought you
this.
created the Mathematica file, right? Print the picture.
No, I don't have it. It's too easy to write it again, so I didn't save it or anything. Yeah. So yeah, I can.
Or you can share the screen like laptop and then show us.
Let me do this.
Okay, I saw it on the net.
Yeah,
I mean, do
these
you want
days things are
me to share the screen?
Yeah, please. Yeah, these days
Just
it
a
is so
minute.
easy to.
Yeah, just 1 minute. Save images. Save. And, okay, now, okay, how do I share it? Just a minute. Yeah, share screen.
Correct.
Okay.
And then there should be an option, I suppose. You
Yep.
want to share the desktop.
Okay.
Oh, there you go.
Yeah.
Is this how it looks like, Shajesh?
Correct. Exactly.
So they have drawn many, right? I mean, this is one.
Yes. This is a whole set of three ellipses of different lengths.
So we will imagine that you have drawn this right now.
Yeah, it should be an outer one. I was attempting the outermost, actually. Yeah, exactly. Yeah.
What is this point F?
Good point, actually. I did not realize that there is such a point. Yeah, as you get smaller and smaller, there is a choice. Yeah, good point. I don't know. Yeah, good point.
Do you think it could be the centroid or something for this triangle? ABC?
I don't know.
No, it's not a centroid because centroid will be somewhere here. No, it's
Oh
not
yeah,
a
yeah.
centroid.
It is not two. It's not 1/3 from the baseline.
Okay.
Yeah.
So this A, B, and C are the 3 points, right?
Correct.
Shajesh?
And there is a discontinuity that doesn't come out very nicely in this diagram. There is a discontinuity in the tangents, slope of the tangents at those 3 points.
Okay, let me show you maybe another.
Yeah, this is a very specific. They're choosing it like to be perpendicular, right angle triangle, sort of.
Okay, let me save image. This and there is. Save images. Okay, so let me show you some other ones which are. Okay, just a minute. Give me. Okay. Share screen. Okay.
Oh,
How's
yeah.
this?
Yeah. That's more reasonable. And again, I should say that these points, when you change the position of these points, then these shapes change drastically. For example, if it is collinear, then they will look like an ellipse, right? So they don't have to be like this. So keep that also in mind. But this is a good representation of what is going on.
Okay.
So very
nice,
good.
very, very interesting, very beautiful.
Yeah.
Yeah. Very nice. Yes.
I cannot understand the curves they have drawn with one, like which are passing through one of the foci.
Yeah.
Which means to say that, I don't know, that the length is like so tight that I don't.
So yeah, there are 3 ellipses which, and then the 3 ellipses for which are three ellipses which are passing through the points, they have a sort of directional anisotropic, as it is the anisotropic, but you can see there is a pointed point, and it seems to rotate counterclockwise, clockwise. Yeah. From smaller to larger, there is a rotation clockwise, and it is pointed at the point, one of the 3 points.
Correct. Yeah.
It has a directional character, like a water droplet, which elongates. The bag of a water droplet, it sort of elongates.
Yes.
Hmm.
Actually, I should say how this originated. Like this investigation, what we were doing is we are one of our collaborators. He found an identity between elliptic integrals, and then we thought, where can we use that identity? And we know that the circumference of an ellipse doesn't have a simple formula like normal all surfaces. It is given in terms of elliptic integral. And since he has some identity for this n that we are talking about, so we thought, can we do something about the circumference of n ellipse just to have an application for this identity? And then we came across this, and we were trying to discover ways to incorporate that into that, and that led us to this.
Just drawing the n-ellipse.
So basically,
first.
can we find the circumference of this quantity, right? Not necessarily related to his identity, but immediately you can think how.
Circumference, of course, in terms of the whatever the 3 points and distances from 3 points, right? Yeah.
Right, in terms of those parameters. And ellipse, it comes out to be the eccentricity that is the characteristic of an ellipse, or a convenient characteristic parameter for an ellipse is the eccentricity. One parameter decides it. But very quickly this generalizes. At least the way we are doing it, it doesn't seem to be converging.
So which website did you find it, Rishi? This one? This image?
Okay. So I just did the website. Let me see. This is some ResearchGate. What I did was I just did a Google search with n-ellipse and clicked on 3 ellipse and clicked on the images. Okay. So this is researchgate.net, this one. And there is one more, which I, yeah, let me show you one more. Okay. Okay. Share screen. Yeah, this is also some kind. Is this a no? What is this?
No, this is something different, I guess.
No. This is nothing.
Actually, this is the path along which we should try. So because we will be working with normal vectors and tangent vectors, a lot of normal vectors and tangent vectors probably have will trace out a ellipse or a.
So here you have a triangle formed by. So yeah, Shajesh, the interesting question that interesting meaning the curiosity that I had was that, so you have a n, right?
Mhm.
The bisector of n1 and n2 is n, right? The normal vector to which
Mhm.
v is perpendicular, right?
Correct. Mhm.
Now, you draw a circle which is tangent to the velocity vector with a constant curvature. Okay,
Huh?
what will that look like?
Imagine it. Yeah.
No, I'm saying, I mean, are you getting my question?
Yeah. So you are saying that n dotted with v.
Yes.
Can I draw those circles?
Can you draw the circle which is tangent to the v?
Yeah.
Okay, with a
Yeah,
constant curvature.
I can draw that here. Okay, let's change my camera again. Let's see. I don't have a board today. You
Hold
can
on.
pin
Rishi, you
this,
can
right?
stop the share.
Ah, yeah,
first.
yeah, sure. Just a minute.
You can pin my video if you want to make it bigger.
Okay, I stopped sharing it.
Yeah. So what we are suggesting is, okay, let's take an ellipse.
So by the way, I'm talking about the ellipse only, not the three ellipses.
Yeah.
Okay?
So I think it's easy to understand that, I suppose, or we have more understanding of an ellipse. Okay. So let's say that's a ellipse. And now we can, like, once I have the ellipse, I'm pretending that I know the normal vector, right? So this is my normal vector, but we want to know it's not just the normal vector, we also need to know so let me draw this better, because so
Unless it is accurate, you won't get the idea.
yeah.
Yeah, see, this is what I meant. Like the angle bisector doesn't make. So maybe if Shajesh didn't.
No, he didn't draw it right.
It has to be an angle bisector.
Exactly, it was not an angle bisector.
What, I made a mistake in the
earlier you drew it in some general direction, right?
Yeah. So that's now bigger, right? So you want the circle to be off that.
Yes, tangent to this n.
That's hard to draw.
I think the ellipse is probably not drawn to proper.
Yeah, that's also true.
Okay, so
but at least I can draw a few of them, and then maybe we can imagine, right? So, okay, let me draw a circle with center in the normal line. Okay, that's my circle there. Okay, that's a bigger circle.
Oh no, but Shajesh. Oh, Shajesh. No. Okay. Sorry. My question was actually ill posed. Because given a tangent, a tangent does not uniquely determine a circle, right? You can draw infinitely many circles to a given tangent.
To a given tangent, yes.
Yeah. So circle is not unique.
No, but this circle is unique. Oh, but then you're trying to tell me that it is based on the knowledge of the ellipse. Yeah. But I thought the way I was interpreting your question is that, can we draw all these circles associated with n? Remember that n, this is not n hat, this is n, right?
Yeah.
N decide the length of the n decides decides the radius of the circle, correct? So can I draw those circles everywhere? And can we learn something of it? Will there be some
surely that circle will not like the way you are showing right now, is it is passing through the one focal point?
No, that is not passing through one focal point. It's just it came out to be like that. No,
that's not a true fact, right? It can pass anywhere.
No,
basically.
I don't. So for example, here this will be somewhere here like this. So this won't even. So this will be like this.
Or to fix certain because as I said, the
so the biggest circle will be here, I suppose, correct?
Why would you say that? Oh, because both of them are
because they're n1 plus n2, right? So this will be 2 times the unit length, and here it will come down smaller, and then it will again grow to 2 times the circle here. Right? Something like that. And probably we want to move this circle so that this becomes tangent here. And then maybe, but I'm just thinking aloud. So it's not going to lead us much, I guess. I've not tried this before.
I suppose that the circles that we get this way will also have some geometrical relationship with this ellipse. Agreed. Because it is born out of the eccentricity of this ellipse, right?
Correct.
They are all, they have to do with, they will be related to the, in fact, so they will also define, you know, the curve which is tangent to the inner parts of the circle. The curve which is tangent to the outer parts of the circle, will it be an ellipse again? I mean, I don't know. It would be an interesting question to pose.
Yeah. It is that, I mean, I do know that because Kepler problem is so popular, that the momentum vector of in a Kepler problem goes about a circle, like not in this space, like the relation is P, like the momentum, the actual momentum of a particle, which is basically velocity, minus there exists a constant P naught. Right, this magnitude is fixed, is a constant. So there exists a fixed momentum. If you subtract, so this is the center of the momentum circle, momentum minus some center point that's equal to a constant. That can be shown in an independent way, like it has to do with the Runge.
For any central force.
For any, not closed any central force, for the 1/r square, Kepler problem. Yes. Kepler problem is very special because it has this Runge symmetry, the SO4 symmetry in the.
Yes.
So yeah. But so I think that is all I have. Yeah, not a very organized.
No, it was very interesting. In fact, you know, I never thought about an ellipse until, you know, today when I heard you. Because I mean, I somehow never thought beyond the, you know, that okay, you can have. See, I mean, one thing is that I think in the 19th century, actually geometry, you know, had a place of pride in all of mathematics and physics. Okay. But I think once the algebraic methods developed, they sort of, you know, overkilled the, I mean, they killed these all geometric approaches. And I think the 20th century, even the schooling is actually schooling, and definitely I think there is no geometry being taught properly in undergraduate college and all that. You know, it's mostly algebraic way of doing things because it's faster. So it kills the intuition, the geometric intuition. Geometry is heavy on your intuition. So if you have developed the geometry, Newton, this entire Principia is littered with everything is geometrically proven, right?
No, I agreed. And that brings us back to the discussion we were earlier having with Bipan, is that geometry is hard to grade, assess. If there is more transparency in grading algebraic quantities, because that's very unique way of going. Like there is an answer, it gives you a fixed answer. Geometry often depends on intuition, and the moment intuition comes in, it's harder to assessment is very hard. Grading is hard. The transparency in the grading is lost. And so it is easy to grade algebra. The moment you grade it, then you use it in exam.
Probably we should not just say it like that it is only the school system that kills geometry. I think the part of that is also the visualization. Like consider that you are going in spaces like beyond, like, I mean, thinking in terms of more parameters than then you can visually assess, right? So like right now, if you have like 3 parameters, we have some idea of like what a shape will look like or visualize things. Now, as Rishi is saying, like, yeah, it's a kind of a chicken and egg situation that you could have developed that kind of visual acumen from the childhood versus you killed the mathematical skills from the childhood, like algebraic skills from the childhood. So yeah, I agree. But like when we teach in engineering mechanics, I mean, the vector calculus and vector algebra becomes like very important because there are less room for making errors. But again, like, yeah, what you say.
But this all, I mean, your statement that it becomes difficult to visualize in a more abstraction, that is also in part, as you said, because of the training, the way we have been trained.
Exactly.
For example, I mean, the 19th century produced such great geometry of Riemann and Riemann at a very early age. And of course, I mean, I'm talking of exceptions now. Riemann, Lobachevsky, and Felix Klein. In fact, Felix Klein, I'm sure you're both aware of this beautiful books that Felix Klein wrote. 3 volumes. This German mathematician on elementary mathematics from higher standpoints. Have you seen that? So it's a, it's a beautiful set of volumes. In fact, I purchased it last year. I want to read them more seriously because when I teach my kids mathematics, so I want to see what. So Felix Klein, he gave a series of lectures to the school teachers, secondary, higher secondary school teachers of Germany. So the title of the volume is Elementary Mathematics from Higher Standpoints. Okay, so it's all about, and I mean, given by the towering Felix Klein. So it's all about all arithmetic, algebra, geometry. But what are the deeper? So all the elementary results, but how do you connect it with the deeper results in mathematics and the deeper understanding of those results? So those were addressed to the school teachers. How to teach mathematics.
Yeah.
Also, I think there is a nice book which I read about, but I cannot find it. There is this Indian mathematician in, I think, Dublin, Siddharth Sen. So, there is this nice book on geometry and topology in physics. Nash and Sen. It's a beautiful differential geometry. I have it right across here. Differential geometry and topology in physics. So Siddharth Sen also wrote a book on how to make mathematics enjoyable for school children. Okay. And it's a very beautiful book. I read the review. Somehow I'm not able to find it. I want to buy a copy, but yeah, so I mean, it's all about, I think the mathematics, the way, and very strongly algebraic. Algebra is, of course, important, I think. But see, a lot of development in mathematics, all the strong development in mathematics happened in, the foundations of all the mathematics was differential geometry, which happened, in the middle half of the last century, where people like Eli Kata, almost single-handedly developed all this. And they were all strong in geometry, actually. So I think that's, it comes in very handy, because geometry actually can connect a lot of deep results. Even also this branch of geometric algebra. See, Prachi spoke about this vector calculus and vectors and all that, right? But I'm sure as you are both aware that this vector calculus and the vectorial way of thinking came about very late, only in the, I think, the dawn of the 20th century when Josiah William Gibbs was the one who, so if you look at the Maxwell's treatise, the Maxwell's equations are not written in the neat vectorial form that we are used to. It's all written in the component form, right? They are just written. So vectors were not the terminology, and in fact, people were motivated, because complex analysis. despite the world being made up of all real quantities, people knew that, when you complexify things, there are some very deep results and connections. You can obtain deep results about the real world by going into complex plane. Because there are some profound results which are valid for, once you have analytic function, a lot of things fall in place. And people wanted, and because complex function is, it's a analogy between a two-dimensional world and a complex representation of a two-dimensional plane, right? And people wanted to generalize this to higher dimensional world. That can we have a higher dimensional complex analog? And Hamilton, spent all his life trying to find a three-dimensional analog for the complex numbers, and he ended up discovering quaternions. And quaternions had a lot of beautiful properties, but then it had a very I think so. It's a division algebra, but so quaternions actually one could not pull it very far. But what we know as vectors is only the vectorial part of the quaternion, right? You have a ijk. The zeroth component is a scalar part of the quaternion. And then you have the coefficients of ijk are basically vectors. So what Gibbs did was to pull out. So the entire development of, because the Gibbs was a very towering figure in physics in the earlier part. So the entire world, sometimes this history, and this is where the Raj's comment about the point of view, the history is the biases of few influential individuals, right? So Gibbs was such a towering figure that it completely influenced the development of the vectorial analysis. But I think there is this famous American physicist, David Hastings.
I don't know, I'm not.
Yeah, so David Hastings, he is a pioneer in, developing this geometric algebra. So he wrote a book, on how a lot of results in all of classical physics can be translated into the language of quaternions and geometric algebra and the Clifford algebra and all that. So, but my point, okay, why I went into this is a tangential this thing, but I'm saying that, so it's a geometric algebra is a beautiful fusion of algebra and geometry. So often, but geometry, what I'm trying to say is that, lot of developments at the forefronts of mathematics, differential geometry, geometric algebra, the algebraic topology and all that. The geometry is actually the unifying, it's a something which the higher dimensional geometry and the non-Euclidean geometry. So the geometry is actually the unifying, it's when it mixes with the analysis and algebra and all that, it leads to some very profound understanding. But unfortunately, the training in school and college is so poor in geometric way of looking at things that it sort of really comes in the way of algebra is actually, very restricting, because algebra is nice when you understand the problem very well. Geometry sometimes can offer you insights, from pure intuition, which algebra you are compelled to deal with the unknowns and the relations, right? So it has to be very, clear and very rigid.
Yeah, but I will say, at least I turn out to be very algebraic. So afterwards, I have to convert it into.
I guess, like Shajesh, that's the same thing. Like most of us turns out to be more algebraic, even students, because we are actually training them that way.
Exactly,
it's consequence
of our training.
So after like a certain grade, you will see that like geometry slowly like got fizzled out completely from mathematics. And unless like you are like actually seeking it out, one probably won't learn it further.
And even in the school, it is taught very poorly. For example, I always found it very hard to prove theorems in geometry, and we were never given a clear picture of, because the teacher also sort of by rote learning, he just taught the proofs. And in the undergraduate, at least my undergraduate training was like there was no proper course in geometry. Anyway, I think we are maybe going way too off the.
Yeah.
Mm-hmm. Yeah.
But yeah, so this was what I
But
had.
it was
Yeah.
nice, Shajesh. Interesting. I enjoyed.
Nice. Yeah.
Okay. So
Nice.
yeah, I think we went 1 hour and 40 minutes already. So yeah, I think
Yeah, we should
yes, yeah.
close it now. Okay. All right. So
Thanks. Yes.
Thank you, Shajesh.
thanks.
Thank you. Be fun.